Hi, my name is Banaz Arzani, and today I'm going to be talking about the session on SIGCOMM that has to do with monitoring and measurements. When I start talking about monitoring and measurements, I usually like to remind people of where the internet started, specifically the ARPANET in 1969, where we only had a small network with only 8 nodes. And so managing this network was relatively simple. Since then, our networks have evolved to the internet, which had over 1 million nodes and a lot of ad hoc edges, and now data centers that are almost just as big. And the problem is, as our networks evolved and as this growth happened, the operators that were building these networks had objectives that didn't necessarily align with optimizing for manageability. What they wanted to do was to maximize profit and to quickly scale to the demand that was increasingly growing towards these networks. And they didn't necessarily pay attention to the complexity that this would add to network management. And because of this, today, network management is hard. I'll give you an example from Azure's data center network topology, which is an example of these networks, right? Today, our networks operate many different protocols, from TCP on our switches to from BGP on our switches to TCP on our servers. We have virtual switches that are running on every single host. And so when something here in these networks break, it's really hard to figure out cause from effect and figure out what was the cause of that problem. It could be because of the virtual switch. It could be because of any of the switches in the network from the load balancer or somewhere on the remote side. And the problem here is our networks have a lot of moving parts. It's almost impossible to get an accurate snapshot at a given point in time. And it's hard to distinguish cause from effect. And while all this is happening, there might also be security breaches, and customers obviously will not like any of this. So because of that, we need measurement and monitoring tools that will help us pinpoint problems when they happen and also help us make better decisions when managing our networks. So these help operators understand what is happening, root cause problems, and then detect security breaches as well. So what are the challenges when it comes to network monitoring? Well, first and foremost, we need to make sure that we have enough resources for the monitoring task we have. And this often comes as a trade-off, because what you want to have is a monitoring infrastructure that doesn't impact traffic that's going through your network. Second, it's not going to be the case that you just have one single monitoring tool running in your network. And one of the things to pay attention to when you read papers might be this: does the paper pay attention to how it's going to resource share with other monitoring tasks for other things? Like, for example, if I'm monitoring to diagnose packet drops, am I paying attention to how much these resources I'm leaving over for detecting security breaches and other things, right? So, and some papers just focus on actually enabling these types of resource sharing. And finally, we need to identify what actually needs to get monitored, what fidelity is actually needed. If you sometimes over capture data, you're wasting resources that can be devoted to other monitoring tasks. And we also need to figure out how to efficiently be able to process the data as it comes in so that we can quickly use it. Because our networks now operate at sub-millisecond timescales. And so if we want to quickly react to changes that happen in our network, we need to be able to quickly analyze these monitoring streams that are coming in. Much has been done in this space. So if you go back into the history of SIGCOMM, you see a whole bunch of papers that focus on different aspects of these challenges that we talked about, from Omnimon to PathDomp, 007, Sonata, DShark, Recoup, Pint. I'm not going to talk about these in detail, but I left the names here for you to go and check them out. Well, what is being talked about in this year's SIGCOMM? So we have 4 papers in this space. The first is in continuous in-network round-trip time monitoring, which monitors network round-trip times by exploiting transport protocol behavior. The second is Flyme1, which enables on-the-fly task reconfiguration for network measurements. What this means is it dynamically reconfigures measurement sketches to adapt to new requirements in the network. Retina analyzes 100 gigabit per second traffic on commodity hardware. So it allows us to analyze measurement traces. So it has to do with the last challenge that I was talking about in the previous slide. And finally, a security-related paper, predicting IPv4 services across all ports, which allows users to discover services running across the internet. So the first paper we're going to talk about has to do with continuous in-network running time monitoring. And what it does is it allows one to discover network round trip times by exploiting TCP behavior. So those of you who know how TCP works, TCP is a reliable protocol, which it checks every packet to be delivered and makes sure that every packet is delivered at least once. And prior work have already actually explored using TCP for different types of network measurements in the past. For example, Roy et al. Had a paper in NSCI 2017 that did that. 007 did that in NSCI 2018. But the real unique thing about this paper is that it attempts to use TCP behavior for discovering network round trip times without having access to the OS in which the TCP protocol is running. So it's doing so from within the network. And it achieves this by exploiting the monotonicity in TCP packet arrivals and analyzing TCP sequence numbers. And it uses recirculation capabilities of programmable switches to enable it to cope with some of the problems that happen if you don't have access to the host OS. So I'm not going to give too much away about how this paper works, but this is kind of an overview of what you should expect from the talk. The next paper we're going to talk about is FlyMon, which enables on-the-fly task configuration for network measurements. So what this means is what it tries to address is a problem of resource sharing across monitoring tasks. We talked about this a little bit earlier. When you try to do network measurements and when you're trying to do network measurements to enable network operators to be able to manage their networks better, you don't just plan for a single monitoring task, but you have multiple different tasks that need to resource share on switches, on hosts, on servers. And so what FlyMon does is it focuses on monitoring solutions that use sketches and dynamically configures sketches such that you can configure multiple different tasks on the same switch and you have enough resources there. And it solves the problem by allowing as much resource sharing across tasks as possible. And to do this, it defines composable measurement units, what they call CMUs, and maximizes the number of compacted CMUs you can install on a switch. Again, I'm not going to give away too much from the talk, but basically what you should expect there is packing some form of Tetris of monitoring solutions on top of a switch, or basically on a host. Finally, Retina here is going to talk about analyzing 100 gigabit per second traffic on commodity hardware. So this has more to do with processing incoming measurement data. And it enables quick analysis of packet traces. So it's basically a better solution compared to prior work such as DShark that also do this, but are more compute heavy. And it solves the problem by pruning unnecessary parts of the trace as early as possible. So basically it allows you to get rid of parts of the trace that you're not going to be necessarily using to answer your query. And finally, it does lazy execution. So it defers expensive operations until they're needed. So these three had to do with measurement for managing, for diagnosing problems. The next paper we're going to talk about has to do with predicting IPv4 services across all ports on the internet. So basically what this work allows users to do is identify services running across various ports on the internet. And it does so by basically doing a more intelligent port scan that doesn't necessarily result in a DDoS attack. And prior work have also done this, but are biased towards common ports. So they're more focused on ports that people use, for example, for HTTP 80 or 443, or let's say RDP ports or SSH port 22, things like that. And prior work also required too much training data. So these are the two challenges that this work tries to address. And what they do is they achieve this by using a bandit-like approach. What that means is they do a probabilistic approach, where they first start with some priors of what ports they think they should scan, and they do a exploration exploitation style. Not exactly that, but a similar style of exploration for identifying which ports need to be scanned next for each individual IP address. And so with that, I invite you to listen to the talks of this session on network measurements and monitoring, and I hope you have a good time at SIGCOMM'.